Dear colleagues, my name is Ruslan Mokaev. I am from St. Petersburg University. Let me present our lecture, Harmonic Balance Method, Tsypkin Locus, and LPRS, Comparison and Counterexamples. The problems of the limited dynamic regime studying are associated with various classical theoretical and practical problems. One of the first such problems was related to the theory of regulation, which required the presence of an operating regime corresponding to a stable equilibrium state. An example of the mathematical formulation and solution of such problem is Vishnegradsky's famous work on the Watt regulator, where for a nonlinear dynamic model of the regulator, linearization in the vicinity of the equilibrium state were analyzed and conditions for its local stability were obtained. However, mechanical and engineering models were soon described, in which stable periodic oscillations appeared, so-called limit cycles. Systematic study of limit cycles and their appearance in applied dynamical systems were carried out in the works of Andronov. He related Lyapunov's ideas of local stability analysis and Poincare's concept of limit cycles with problems in analysis of discontinuous engineering models, which resulted in development of the theory of oscillations. In 2009, Leonov and Kuznetsov proposed a new classification of oscillations, which reflected the engineering approach to the analysis of oscillations emergence and became a catalyst for the discovery of new oscillations in known systems. The oscillation is called a self-excited oscillation if its Bayesian attraction intersects with the small neighborhood of an equilibrium. Otherwise, it is called a hidden oscillation. One of the most notable tools in Andronov's theory of oscillations was the point mapping method, or sometimes it is referred as the point transformation method, which allowed to compose differentiable almost everywhere solutions for nonlinear systems of low order with piecewise linear nonlinearities. The point mapping method could be applied also for systems of high order, but resulting equations will be transcendental and therefore they cannot be solved analytically. Also note that it took 45 pages to rigorously solve the Vishnegradsky three-dimensional problem. But what is actually a solution of a discontinuous dynamical equation? Various approaches to define solutions have been proposed since 1930s. In our research, we used the one introduced by Filipov, who developed the first substantive theory of differentiable equations with discontinuous right-hand sides. One of the first general methods for analysis of periodic oscillations and global stability was the harmonic balance method, which originated from the works of van der Pol, Krylov, and Bogolyubov. The nonlinear system with signum nonlinearity harmonic balance equation takes the following elegant form. The classical harmonic balance method is an approximate method for analysis of periodic oscillations, and therefore it may give incorrect results. This method was further developed and extended in various studies. For instance, a method introduced by Leonov and Kuznetsov allowed to obtain initial data of stable periodic solution for a particular class of Fourier systems. Let us now consider the extensions of this method for relay systems, namely the Tsypkin method and the locus of perturbed relay system method, or the LPRS method. These methods were developed in the works of Tsypkin and Boiko respectively, and later we will show that they allow to yield more accurate results on prediction of the loss of stability and existence of oscillations compared to the harmonic balance method. That may actually not show potential existence of an oscillation at all. Moreover, it can be shown that it is possible to obtain initial data for visualization of periodic oscillations. In addition to determining the presence of oscillations, it is possible to analyze the stability of these oscillations. The harmonic balance method was extended by Goldfarb and Kochenburger in their papers in the late 40s. According to their method, stability can be determined by analyzing the Nyquist plot and the behavior of the negative inverse of the describing function. This approach is used to analyze stability of oscillations that are found by the harmonic balance method, which deals with nonlinear systems of general form. For relay feedback systems, corresponding theorem on stability of symmetric oscillations was introduced by Ostrom in 1995. A little later, a similar theorem was proposed for asymmetric oscillations. To illustrate the difficulties in analysis of oscillations, we first consider the Keldysh model of flutter suppression by hydraulic damper with 2 degrees of freedom. In 1944, he published a paper where he used the harmonic balance method to analyze the emergence of oscillations and estimated the boundaries of global stability. Wherein Keldysh understood that he was using an approximate method and the results are not mathematically rigorous. To illustrate the problems in analysis of oscillations using the harmonic balance method, we consider Keldysh model with the following values of parameters. According to the harmonic balance method, there is one unstable symmetric periodic oscillation. But according to the Tsypkin and the LPRS method, there exist 2 unstable symmetric periodic oscillations. However, the Tsypkin and the LPRS method also have limitations. To illustrate these limitations, let's consider the same values of parameters and using numerical modeling from the vicinity of the rest segment, it is possible to localize 2 self-excited limit cycles. And these oscillations cannot be found using the Tsypkin or the LPRS methods. Further, we consider the other values of parameters for this model. According to the harmonic balance method, there are no periodic solutions at all. But according to the Tsypkin and the LPRS methods, there exists one stable symmetric periodic oscillation. And as for the previous parameters, we can apply numerical analysis and obtain initial data of 3 hidden periodic oscillations. One is symmetric and the others are asymmetric. And finally, considering the following values of parameters and applying numerical analysis, it is possible to visualize chaotic solution which cannot be found using the harmonic balance method, the Tsypkin method, and the LPRS method by design. The second example is a 3-dimensional Atherton system with D as a parameter. We consider 2 values of this parameter, and in both cases, the harmonic balance method, Tsypkin method, and the LPRS method shown the existence of one unstable symmetric periodic oscillation. However, in the first case, D equal 1.23, there are also 2 unstable asymmetric periodic oscillations and 2 stable asymmetric self-excited periodic oscillations. In the second case, besides unstable periodic oscillation, there are 2 self-excited chaotic oscillations. An interesting connection can be observed between these methods and famous Eiserman and Kalman conjectures on global stability, which are as follows. Suppose all the following linear systems are asymptotically stable. Then all nonlinear systems with particular conditions on nonlinearity function are globally stable. According to the harmonic balance method, these conjectures are true, but multiple corresponding counterexamples were constructed. We can also construct a counterexample to the Kalman conjecture by performing numerical continuation procedure of the Keldysh model. As a result, we obtain a system that satisfies conditions of Kalman conjecture, which has stable equilibrium state coexisting with two periodic oscillations and one chaotic oscillation in the phase space. In conclusion, we note that difficulties of analysis of oscillations in Luria system with one scalar nonlinearity are connected with the problems of localization of hidden oscillations and possible birth of chaotic regimes. Also, analysis of the Keldysh model demonstrates the advantages and the limitations of the harmonic balance method, the Tsypkin method, and the LPRS method. The harmonic balance method may not predict existing oscillations. Also, the Tsypkin method and the LPRS method are able to find symmetric periodic solutions with exactly two relay switches per period. Therefore, they are unable to find both asymmetric solutions and solutions with a high number of relay switches. And these oscillations may be self-excited or hidden. And all these methods cannot find chaotic oscillations by design. Results of this paper may be used for the further development of the Tsypkin method and the LPRS method. And finally, localization of hidden oscillations allows one to estimate the outer boundary of global stability. Results of our research are presented in the following papers. Thank you.